All right, here's part 2 of Unit 1 worksheet. This is the second page of the worksheet. So if you're looking for questions 1 through 4, that's in part 1. This is going to be questions 5 through 8. So let's begin with scientific notation. Convert the following numbers into scientific notation or vice versa. So for this one, 145.6, if we want to convert that into scientific notation, we need to move that decimal place until it's between that 1 and the 4. So we're going to move it 2 spots. And we're going to write out all of the digits because there are no zeros to the left of the decimal place. Okay, in fact, there are no zeros at all. So we need to include all of those numbers. 1.456, since we moved it to the left 2 places, we need to do times 10 to the second. Okay. This number is bigger than 1, so that's going to mean this number is positive. All right. Next one, B. This is 1, 2 with 1, 2, 3, 4, 5, 6, 7 zeros, and then we have an implied decimal point. If there's no decimal point there, you put one there because it's implied. And then we're going to move this all the way to between the 1 and the 2. 1, 2, 3, 4, 5, 6, 7, 8. So we moved it to between the 1 and the 2, and we moved it 8 places to the left, so that means it's going to be a positive 8 there. Another way you know it's positive is this number is much, much larger than 1, so that means this must be positive. Okay, here's one going the other direction, 5.68 times 10 to the 8th. Well, we're just going to do this backwards, essentially. We're going to write out 568. You can even put the decimal place there if you want. And then we need to move it 8 places. 1, 2, 3, 4, 5, 6, 7, 8. Put a 0 in each one of those dips. Okay, and if you want to rewrite that out, that's fine. 5, 6, 8 with 6 zeros. Okay. Again, positive number means it's going to be bigger than 1. How about a negative number here? A negative number. If we have a number that is smaller than 1, meaning it's a decimal, that means that our exponent will be negative. Here's our decimal place. We need to move that to the right all the way until we reach the first non-zero number. And we're going to put it after that first non-zero number. So 1, 2, 3, 4, 5. Okay, and there it goes. We're going to rewrite this 8.76. Since we moved a decimal 5 places to the right, we're going to put a negative and then the 5. All right, E, going the other way, where we have scientific notation, going to convert it into regular numerical notation. So 9.75 times 10 to the negative 9. So I'm going to go ahead and write out my 975 here. And I know I need, my decimal is right there, I need to move it 9 spots to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to put a 0 in between each one of those peaks, or in the dips. Okay. And I'm going to stick the decimal right there, and I'm actually going to put another 0 behind this decimal. So I didn't quite leave myself enough room here. Let me rewrite that just to show you. I've got 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros and then my 975. You always want to have a leading 0 here. This just tells the reader that this is a decimal. It's very easy to identify 0.0 as opposed to just that. It can be easy to miss this, or maybe you didn't make the dot big enough. So always when you write decimals, put a leading 0 here, then the decimal, then you write out the rest of it. Okay, here, this one here, 450,000. Remember, there's an implied decimal point there, so I'm going to go ahead and move that 1, 2, 3, 4, 5 places. Find that first non-zero number. 4.5 times 10 to the 5th. Again, this is positive because the number is bigger than 1. Okay. Number 6. Explain the difference between accuracy and precision. In a few sentences, come up with a unique example of when it might be important to distinguish between accuracy and precision. Using your example, what are the implications of understanding this distinction? Okay, I'm just going to talk through this one. I'll write out just a short definition of accuracy. Accuracy is how close a measurement is to the true value. Now, when we make measurements, we want them to be as close as possible to the true value. And so we want to be accurate with our measurements, but we also want to be precise. Okay, precision is how close each measurement is to each other, or how close measurements are to each other. Okay? If you count the number of people in a room and you come up with 3 very different answers, you didn't have very good precision. And you also probably didn't have very good accuracy. But if you count the number of people in a room and you count maybe there's 151 people in the room and you count that same number 3 times, that means you had great precision. And hopefully your number is accurate if you did it 3 times. There'd be no way to know that without actually knowing how many people are in the room, but the point is you want your measurement tool to be very precise. You want it to be repeatable. You want the measurement to have good repetition. So this could be, an example of this in the lab might be, say, a graduated cylinder. Okay, here you have a graduated cylinder. Terrible drawing, I know. And you've poured a certain amount of water in that graduated cylinder. Well, if the graduated cylinder is properly calibrated, it's going to deliver an accurate amount of liquid. But you, as the user of that instrument, you as the user of the graduated cylinder also need to be precise in your measurement. So if you're measuring 10 milliliters, you need to get the water level as close to that 10 milliliter mark as you can each time. So that would be an example of precision. Accuracy has more to do with the not only your use of it, but also the design of the instrument itself. All right. Moving on to number 7. I don't know why this got so dark all of a sudden. Let me see if I can brighten it up here. Okay. All right, perform the following conversions. Okay, I've got 6 of them here, and I'm going to walk you through each one. Starting with A. Remember, you need to have